Hi, I'm Professor Goins. In this video, I'm going to look at a technique for solving differential equations where we use what's called an integrating factor. All right, so consider a first order linear differential equation in standard form. So that means that the order of the derivative, the highest order of any of the derivatives is 1, and then the standard form means the leading coefficient or the coefficient of the derivative term is 1. What I'm going to do is multiply both sides by this function down here in red. Mu of x is e to the antiderivative of p, so the antiderivative of the coefficient of y, which we call the integrating factor. And before I do that and write out those details, let's take a look at the following. If I differentiate the following product, y e to the antiderivative of p of x dx. Product rule says derivative of the first factor, so dy dx times the second factor, so that's where this part comes from. Derivative of y times the second factor, plus the first factor, which is y, times the derivative of the second factor. Derivative of the second factor here, since this is an exponential with a function on the inside, we would use the chain rule, so that would be the derivative of the exponential. The derivative of the inside function comes out as a factor. This being the antiderivative of p, the derivative would be p itself. So keep in mind that the derivative of that product gives me this expression right here. Okay, so we're going to use that here in a moment. Back to the differential equation. I'm going to take this first order differential equation and I'm going to multiply by this function right here. Okay, so doing so gives the following. So I took integrating factor and I multiplied by the derivative, so that's what I have. Now I'm going to multiply it by this. So plus p of xy e integral p of x dx. On the other side, I would have f of x times the integrating factor. So I've got f of x e integral p of x dx. All right, now look at this expression right here on the left-hand side of the equation. It matches what I have up here. That means that I can combine those two terms as the derivative of a product. So these two terms right here is equivalent to the derivative of y e antiderivative of p of x dx. And then the other side would be f e integral p of x dx. So this is what the integrating factor does, is it allows me to write the left-hand side as the derivative of a product rule. From here, I can undo this by taking the derivative or antiderivative of the other side, and then I just divide by this to isolate y. So in other words, to isolate y, I have to get rid of two things, this operation and this factor, okay? So let's walk through an example and see how this works. Okay, so here's a linear first order differential equation, but notice it's not in standard form because I have a factor of x out front. So what I'll do is I'll start by dividing through by x. That will give me dy dx plus 1 over xy is equal to cosine of x. So you can see that this differential equation right here has the form of this one in green, okay? What I have to do then is multiply by the integrating factor. So let's find the integrating factor in this case. Remember that p of x is the coefficient of y. Okay, so p of x is the coefficient of y, and that's what I use inside the integrating factor. So I take the antiderivative of it, and that's going to be the function inside of the exponential. So the integrating factor in this case, mu of x, is e to the antiderivative of 1 over x dx, which is e to the natural log of x, which is x. That's what I'm going to multiply the equation by. x dy dx plus y is x cosine x. It just so happens in this example that the equation I get by multiplying by the integrating factor was the equation we started with. That doesn't really happen very often, but it could happen, but it just so happens that this is a case where that, where that occurred. All right, so then the left-hand side here, we can rewrite this as the derivative of, so let's look over here first. It's the derivative of y e to the antiderivative of p. So that's going to be y, and then the integrated, it's just y times the integrating factor. So y times the integrating factor, which was x, is equal to x cosine x. Let's double check real quick. If I take the derivative of the first factor, I get dy dx times x, so that's this term here, plus the first factor, which is y, times the derivative of the second, which should be y times 1, which is this term right here. So then, in order to undo this, I'll take the antiderivative of both sides. So that says that yx would be the antiderivative of x cosine x dx. So to take the antiderivative of x cosine x, that's going to be an integration by parts. So let's set up our integration by parts table here. So I would have, let's say, u, du, dv, and v. Okay, so in this case, we'll choose u to be x, so du would be dx. dv then is the rest of the integrated with the differential, so that would be cosine x dx. Antiderivative here would be sine of x. And so remember the integration by parts formula says I take the product of u and v, and then I subtract the integral of v to u. So here's what we have so far. Yx is equal to, so that'd be uv, so x sine x, minus the integral of v du, so sine x dx. Okay, then yx would be x sine x minus antiderivative of sine would be negative cosine, and we could put a plus c there since that's an indefinite integral, and then minus minus makes that a plus, and then just divide through the whole thing by x. So the solution to the differential equation is this: sine of x plus cosine of x over x plus that arbitrary constant c divided by x. And this right here again is the solution to that differential equation.